In this exercise, we will be performing k-means clustering analysis. And we're going to be addressing two issues of k-means clustering. The first issue, how do we interpret the meaning of the cluster when the dimensionality of the data is more than two variables and we cannot plot the clusters anymore? The second is, how do we determine the number of clusters, which is one hyperparameter that we need to set, pre-specify for the algorithm to operate. The dataset that we're going to work on is called the utilities dataset. And this dataset provides information about different utility companies in the US, as well as some features related to these companies. The data dictionary is provided for us here. If we load the data, this shows the five first observations in this dataset. Now, the goal of this analysis is to group these companies, these utility companies, in clusters based on their similarities. And then by examining the clusters, we can probably try to understand some of the hidden associations patterns. What makes some utility companies similar to some other companies versus the others? We don't have a specific outcome variable, and hence we're doing clustering analysis here. We basically want to look at all of these feature variables and try to figure out how they relate within these different utility companies. So we're going to perform clustering, and we're going initially to set two clusters and try to interpret the results and figure out what these clusters mean. Second, we're going to use 6 clusters and try to figure out what those clusters represent. However, in setting this hyperparameter, we want to be more systematic in doing so. So we're going to use the inertia criteria to determine the optimal number of clusters. Now, the inertia criteria is basically the criteria that the k-means clustering algorithm used to set the centers of these clusters in its expectation maximization cycle. It's basically the average distance between the cluster center and all of the different observations that belong to this cluster. Now, obviously, the algorithm chooses cluster centers to minimize these distances, but we can use these distances as a measurement of the cohesion of these clusters. Meaning, let's imagine two clusters now. If we have two clusters, but those clusters are grouping observations that are further apart, we would expect that the distances to be larger than, for instance, if we use a third cluster that groups a bunch of these observations together. Think about when outlier, for instance, can increases this within cluster cohesion a lot, because now you're computing the distance between each point in the cluster and this outlier. If you put this outlier in its own cluster as an extreme case, you would really minimize these distances within the two clusters. So our criteria here is we look at the inertia of the cluster and we want to minimize it. We want clusters that are cohesive together. So we're going to run the algorithm multiple times, and when we increase the number of clusters, we will decrease inertia, but we want to decrease the inertia. At a certain point, there will be decreased differences in the inertia, so we don't have any return on our investment in using more clusters. Let's start with question 1 and question 2. So first, we have this data here, and we don't care about the company, but we don't want to throw companies. We want to still keep the company information here. So what we're going to do here, we're going to set the index to be company. So setting the index is doing us two things. It's basically taking out company from being a column, so it's no longer a feature, but it's also keeping it for us for further examination once the clusters are created. So we set the index to be company, and then we create a k-means clustering algorithm here. The number of clusters here will be 2, and I'm going to start from a random state. The random state should be a random number generator seed. So I'm going just to put 0 here so that when I recreate this notebook, you'll get to see the same results. Let's call this one k-means. and that will basically create the k-means here. Now we can take a look at the parameters of the result, the k-mean algorithm, but we can also group this data using the result. So, if we do k-means here, dot labels, that's going to give me a label for each one of the observation. It's taking a while, so let's see. So we forget the crucial step of fitting the data here. So we want to fit utilities df, and now we get the k-means estimated, and those are the labels for our data point. So what we can do with those labels, we can actually do a group by. So I can take a look at my data here, for instance. So let's call utilities df dot group by k-means dot label, and this will associate each one of these observation with its k-means. Now, what I'm looking here, I'm basically looking to grouping the name of the companies here, and the name of the companies here are on the index. So I'm going now to sneak back the index to being a column, because I want to take a look at this company column again. So what do I do with this one? I basically want to see each company, what the companies grouped together in these labels. So there are different ways to doing it. Company is basically a text column. So what I can do here, I can apply list to make a list of company for each one of these clusters. So for cluster 0, I have these companies: Florida, Idaho, Nevada, Puget, Texas, and I have more companies in one. Obviously, I need to increase this. If I want to see this one as a complete list, I can put the values here. Take a look at the second cluster, cluster 1, and that's going to give us the values here as a list. Okay, I think I need to convert it to list and take a look at the second component here. Excuse me. So those are the companies in the second cluster here. Okay. Now the question is now asking me to do this, to interpret these clusters. So I cannot really visualize these clusters because I have multiple variables here. I have 1, 2, 3, 4, 5, 6, 7, 8 dimensions. One way is to create a visualization for each combination of the two, but you can see that the task is already daunting. So what I'm going to do, I'm going to create a numerical summarization of what these clusters mean. This basically kind of very related to the same idea of creating a group by the clusters. But instead of looking at the name of the companies here, I don't care about the name of the companies anymore. Once I do the grouping, I want to get information about these variables. So I'm going to do the averages here. It's called .mean. And you can see here that I have the average of each one of these variables for each one of the clusters. So then I can examine the differences here and try to figure out what they mean. So in terms of fixed charge, there is no big difference here. ROR, no big difference. The cost, there is some difference, but on a baseline, it's not that big. 10 over 100, that's less than 10% probably. The factor load is not that a big difference. Demand growth, there is some difference. It's not, so that's probably more than 10% of a difference in between these two. But if you take a look at the sales, there is like a big difference between 14,000 and 7,350. So if you take a look at the sales here, this is the kilowatt per use per year. But basically differentiating between big and small companies here. Interestingly, if you take a look at the difference in nuclear here, which is the percentage of nuclear, you can see that the larger companies, the companies have more sales. They don't rely so much on nuclear compared to the companies that have low sales. And if you take a look at the list of the states, not the states, the company names, that give you an idea about the states, that can tell you which these companies that use a lot nuclear power operate in some of these areas. The fuel cost is also a big difference here. You can see that fuel cost is much lower for the companies. Understandably, they do not use nuclear powers. So here you can see there is a relation here. Maybe the fuel cost is driving the dependency on nuclear power in these companies. Well, the other interesting insight is that although these companies use less nuclear power, they serve more population or more electricity usage, to be more specific. So it seems that the two clusters really picked on this demand side, the aspect of power generation of the companies, but nothing about the financials information here. Understandably, if we increase the number of clusters, we're going to find more differences. So let's take a look first at the inertia here before we move in and override this k-means. There is an attribute called inertia, which gives us this sum of differences, square differences in between the observations and the centers of the clusters. So obviously this is one value, and without a baseline we can't say anything here, but it's already a big number. What we're going to do here, we're going to increase the number of clusters to 6. That's basically the same code here, and again, it should have probably isolated in a function, but for the sake of this exercise, I'm going just to copy and paste. We fit now, and then we can do the same to get the companies in different clusters. So we have 6 clusters now, and we have more fine, granular clustering of these companies. Once again, what do these clusters mean? One way to look at that, we can look at the average value of each one of variables per cluster. And here you can see that now these clusters understandably are picking on different of these variables here. So if you take a look at variables such as fixed charge and ROR, although the magnitude is different, it's not that big, you can see there are some differences across these companies here. And there are also differences in between the companies across the other factors, including the ones that we looked at. So when you look at nuclear now, you can see that some of them don't rely on nuclear at all, which is companies in cluster 1 and company in cluster 3 in that example. So, but again, interpreting these clusters is now more difficult because we have 6 of them. So then, this is the question here, what's the optimal number of clusters? Too few clusters, and we risk kind of missing on some of the patterns in the data, and we get a very coarse grained understanding of the differences in between these clusters. Too many clusters, and we can't really explain the differences across these clusters. So what's really the difference in between cluster 1 and cluster 3, for instance? It's probably the demand growth. Both of them don't rely on nuclear, but maybe the demand growth, but there are also other factors. So we want to be systematic in setting this value, the number of cluster, the hyperparameter. And we're going to use the inertia here. If you take a look at the inertia, now you can see that it has decreased. So in between 2 clusters and 1 cluster, we have decreased the inertia. But again, we don't have our baseline is 2 clusters. Did we increase it enough? So what we're going to do, we're going to be more systematic in doing this. And we're going to be more systematic by creating k-means clustering with a range of values. So this basically creates a clustering from 1 cluster, which doesn't make a lot of sense, but may serve as a good baseline, to 6 clusters here, because it ranges from 1 to 7, so 7 exclusive. In each one of the steps, we're basically creating k-mean clustering and running the algorithm, fitting the data on the same data here, the data that we have, with the same random state. And then we're getting the inertia and normalize it over the number of clusters and appending it to this list inertia. Once we're done, because our interest here is in selecting the number, we're going to visualize it. So we're going to create a data frame that has 1 column, which is the number of clusters, and the second one, which is the inertia. And then what we can do here, we can plot it as a line plot. Now, if you do this, you can see that Well, we started with one cluster with a very high inertia, which is understandable because you're looking at all of the points. It dropped significantly when we do two clusters, so obviously two clusters is getting us something. But what's interesting is that it drops further down when we have three clusters, but our benefits of adding more and more clusters start to diminish. In 4 clusters, there is a difference here, but that's not as big as the difference in between 3 and 2. And we have diminishing return from now forward. So probably just looking at this number, maybe 3 clusters is a sweet spot in between 2 and 6 or 2 and 10. So that will give us some more granular understanding of the data, but it will not overwhelm us with a large number of clusters for us to figure out what they mean. So let's do this. Let's run 3 clusters, and I'm going to copy the code for the average per cluster, and this should tell us, I forget to fit the data again, utilities df, that should give us some differences across most of the variables, and with 3 clusters we can still understand these differences here. So we can see here, when you take a look at the demand side again, is that we have companies that rely heavily on nuclear, in between and at all not at the nuclear, and there is a difference in the fuel cost, difference in the sales, as well as the demand growth. But there are also some differences in the variables here. For instance, if you take a look at the variable ROR, which is the return on capital investment, you can see that the companies that do not use nuclear have lower ROR compared to companies that tend to use more nuclear. But that's not a deterministic relationship, because even the companies that use some nuclear have a more ROR, so probably depends on other factors now. So using this inertia as a criteria is really helpful, because it enables us to be more systematic about setting this hyperparameter, which is the number of cluster.